Okay, so let's get going here with 4-3 notes. We're going to talk a little bit here about energies. A lot of this should be review. However, at the end of the section, we are going to talk a little bit about vectors and some stuff that you should have seen in pre-calc, but you maybe haven't seen for a little while. So probably the last part or two of this video will be pretty helpful to look at. But hopefully most of the first portion is just review of some of the basics of energy here. But anyway, we know that total energy for an isolated system is conserved as long as there's no outside force acting, right? So as long as it's an isolated system, as long as there's no outside forces acting, then we know that the initial energy is equal and opposite, or not equal and opposite, but just equal to the final energy of the system, right? So we know that that relationship is true as long as the net force on the system is zero, right? So that is one thing to make sure we're always pretty confident with. As long as there's no net force, the system conserves energy. All right, what do we know about work? Well, go back if you can to last year, right? We know that work equals force times distance. But what has to be true about the force and the displacement, right? In order for work to occur, the force and the displacement have to be the same direction, right? So if I have a force going this way and a displacement going that way, or vice versa, then how much work is done in this scenario? Well, that's kind of like if I carry a board, right? If I'm walking across the room with my board, I'm exerting a force upward, but I'm walking side to side. That would be an example where we don't do any work. So make sure you're pretty comfortable with that notion again. The force and the displacement have to be the same direction for work to occur. The other way that we can work with work, if you will, is we can relate work to energy, right? So work is just a form of energy, which means it relates to any type of change in energy. So an easy example of that would be if I have an object on the ground and I ask you how much work does it take to lift the object 5 meters into the air? Well, all I really have to do is figure out what's the change in potential energy, because however much potential energy that object gains, that's how much work I had to do on it. So that's another key relationship. This is one that oftentimes maybe doesn't jump out right away. But if you ever get stuck, try relating the work to a form of energy, whether it's potential or kinetic, and see if that maybe helps clean things up from there. But anyway, so some of the basics, hopefully, of work, right? When is work positive and when is it negative? Well, work is positive, right, if the force and the displacement are both going the exact same direction, right? So the work is positive if the force and the displacement are the same direction. They're negative if the force and the displacement are opposite directions, right? So that's when it's negative, and then they're positive when they go the same direction. So again, another basic concept there, right? The other thing to think about is if the work is negative, then if the work is negative, isn't my system going to be losing energy? So most of the time in a situation like that, we'd be losing energy, we'd be losing kinetic energy, so the object should be slowing down, right? Which makes sense because if the force is going the opposite direction of the displacement, shouldn't the object be slowing down? So anyway, a few of the key concepts hopefully from last year. I don't think any of that probably is too mind-blowing for you guys, but good stuff to review as we move forward. So another perspective of this, so again, kind of what I said there at the end of the last slide. Work is positive when the environment does work on the system and the system's energy increases. So if something's happening to where, right, maybe if I take an object, if I release that object from rest, if the object is my system, then we know that the force of gravity is pulling down on it, and if the object is allowed to fall down, then since the force and the displacement are the same direction, they're both going downward, my system, my object, would be gaining kinetic energy, and therefore its energy would be increasing. So that would be maybe a simple example of that. Work is negative when the system does work on the environment, and the system's energy decreases. So basically this is the object is expending some energy, right? So an example there would be the fact that maybe as an object is sliding, if it has a certain amount of kinetic energy but there's friction involved, then the box is actually converting some of its kinetic energy to heat, right, due to the friction, right? So that would be it's giving off some of its energy to the environment, and therefore the box's energy would be decreasing. But again, the key relationship, we'll see some more of those conceptual examples as we go through the chapter and the homework, but the key concept here is work is simply equal to any type of change in energy. So if we know there's a change in kinetic energy or potential energy or thermal energy or all of the above, work is just going to equal the total change of all of those energies. Right. So you may see a few examples like that, but hopefully nothing you guys can't handle. So I certainly don't think it would be. But anyway, let's look at this first example. Pretty easy one here, I think and hope. But a child slides down a playground slide at a constant speed. The energy transformation is which of the following, right? So if the kid's going down the slide at a constant speed, now if we think about this, right, the constant speed is important because what's that tell us about energy? Well, if he's traveling at a constant speed, he or she is traveling at a constant speed, then my kinetic energy is not changing, right? Since I know that the kinetic energy would be 1/2 mass times velocity squared, and the kid's mass presumably isn't changing, and its speed's not changing, so the kinetic energy is not changing. So if there's no change in kinetic energy, right, what type of energy am I losing? Well, as the kid goes down the slide, we are losing potential energy, right? We're losing potential energy due to gravity. And if that's not going to kinetic energy, where is that going? Well, the only other source that it could be going to would be friction and or thermal energy, right? And so that's really what's happening then is I'm taking potential energy, which a lot of times they use that U to represent the potential energy. So my potential energy is going to not kinetic energy, but to thermal energy, right? As the child slides down the sled there or down the ramp there, some of their potential energy, all of their potential energy is converting to heat due to the friction between the slide and the child. So that's really the sense where we'll see this new thermal energy. For the most part, it's any type of energy that we're losing due to friction, right? So on some of those problems like we used to have where you'd have a box that was moving with a certain kinetic energy, if you know that there's a certain amount of work done by friction, friction is simply going to make it lose that much thermal energy, right? So if I told you that this box started with 20 joules of kinetic energy, but then there was 10 joules of work done by friction, then the final energy would be 10 joules of energy, right? I would do 20 minus 10 to figure out what's left. So we'll see a few examples like that as well. But again, I don't expect that to give you guys too much trouble. Before we get into several examples and several of the parts that I don't think you guys will have too much trouble with, let's go back though and do another example, kind of like what you did in the last section where we had to do a few of the integration type stuff. So I'm actually going to show you the work kinetic energy. I'm going to show you the relationship between work and kinetic energy. But I'm going to show that by starting with just force equals mass times acceleration. So I'm going to approach this very similar to what I've done in the last few. Right? So for the last few, the big step was realizing that the acceleration is really just my derivative of velocity with respect to time, right? So if I substitute that in, so I've got force, and obviously they've got the sub x in here. I won't keep that in there too much just because I don't want it to get overly complicated. But the force sub x would equal mass times, technically this would be dv sub x, and then dt doesn't need the x because time isn't a vector, it's just a scalar. But technically that's what it would look like. I'll probably drop that x just so it doesn't get too complicated and just so my variables don't get jumbled. But again, my first step, I'm just breaking up acceleration as the derivative of velocity with respect to time. So then just like I did in the last example, right, just like I did before, I can actually take dv over dt and break it up into a third-party variable. And since I want to relate work, which is force times distance, to kinetic energy, which is mass times velocity, right, time doesn't pop up in that equation at all. So I want to get rid of this variable of time. So instead what I'm going to do is break it up like we've seen, where I'm going to do dv with respect to dx times dx over dt, and then break that up as such, right? So what do we know about dx over dt? Well, again, the important thing, hopefully you're starting to get comfortable with that, but this is really then just the velocity, right? So my next step here, my net force, my force in the x direction would be equal to mass times dv over dx, and then times, again, dx over dt, which is really just my velocity. So just like we've done before, if I isolate the variables onto separate sides, so if I multiply both sides by dx, if I multiply both sides here by dx, then I have the force with respect to the x direction, dx, equals mass times velocity, dv. Right? I reordered that there. I just moved the velocity up front, and then I had the dv left because the dx canceled out. So hopefully, pause obviously for a second if you need to, but hopefully everybody's pretty comfortable with this. So now that I have the dv and the dx on separate sides, now I can integrate this function. Well, at this point it looks very similar to what we've done a few times before. Right? If I integrate both sides, I'm integrating it with respect to the variable. So on the left-hand side, I'm integrating it with respect to x. So that's why the f sub x, this x isn't really a variable, right? It's just a descriptor for the force. So I don't have an x variable, so I can think of that as x to the 0th power. When I integrate it, I'm adding 1 to that power. So on the left-hand side here, I'd get f times x, and then plus my constant of c, right? Plus some constant as I integrate that function. On the right-hand side, I'm integrating with respect to velocity. So then I've got my velocity, I've got my original velocity here, which is to the 1st power. I add a power of 1, and then I divide by that new power. So that's where I get my 1/2 mv squared, which again, hopefully you're starting to get pretty comfortable with that one. And then on this side, I'd have a plus c as well. You want to call that c2 just to distinguish the fact that it's a different c, but we do get that as well. So in any case, the big principle that I want you to start to realize here is I've got force times displacement on one side, and I've got my velocity on the other. So really what we would see here is then if we had some numbers to substitute in, that once again there's a relationship between force times displacement and my kinetic energy, right? So just like I've done before, really if I think about the change in force times displacement minus 1/2 mv squared, the difference between that should always be some constant number if I move the c's to the right hand side. So the significance here is just the fact that I've always got this relationship, right? If the kinetic energy goes up, then that's coming from my force times my displacement. Okay, so anyway, I do want you guys to be comfortable kind of deriving that just to see the relationship that exists. But beyond that, it's hopefully nothing too tricky. Again, it's the same type of integration we've seen a couple times before. The other reason that I do want you to be comfortable with this is I want you to realize that if I give you, and I believe I've mentioned this before, but just to recap it if I have, right? If I give you a force versus a displacement graph, I want you to be very comfortable interpreting that graph, right? So if I give you a graph that's a nice straight line or a set of straight lines, then it's not too bad to work with. So if I give you force versus displacement, what does the area underneath that curve represent? Well, force times displacement, right, would be work. So the area underneath this curve would represent either the work or the change in energy, right? So it would be a work or a change in energy. What if I gave you a function that wasn't a linear function? So what if I gave you some function in terms of x that was like x to the 3rd plus 2x plus 5, right? If I gave you this function and I asked you something about the area, how do we get there? Well, again, the key is the fact that if you think graphically, if I think graphically about this, I know that the area, or the work, excuse me, is the area underneath the curve. So because of that, that should be jumping out to me as the integral, right? So the relationship I want you to be comfortable with is if I ask you about the energy or the work, right? So whether it's the energy of x or whether it's the work done by x, if I ask you about these and I give you the force function, then we should be thinking I need to find the integral. I need to integrate that function. So all I would do is I would integrate this function, and then that would be my function representing the work. So obviously as you go through the homework, as you go through the reviews, you'll see several examples like that just to get us comfortable with it. I certainly hope that's not too terribly difficult. But the way that I always kind of keep perspective on that is I think graphically. So again, if they give me force versus displacement, I think about the graph and I think what is the area, what does the integral represent, and what does the slope represent. Now in this case, what would the slope represent? Well, the slope would be force over displacement. Does that have any physical meaning for us? So certainly think about that a little bit if you would. But that's the first question I want you to always ask yourself, right? What does the area of that graph represent, and what does the slope of that graph represent? For any graph that I may give you. But anyway, enough on that. Moving on with a few examples, and I may have to stop this part here pretty soon, but I think I can get this one in, because this one just pretty well summarizes what I just said, right? So force versus displacement, again, they sometimes use S instead of X, but it's really the same deal, right? So it's in meters, it's my displacement. The area underneath that curve is simply the work, or the change in energy, right? So just be comfortable with that relationship. Again, realize that the work is the integration of the force versus displacement function. It is something to be careful about because we will in the next chapter talk about force as a function of time. So you do need to be very careful about those too, but hopefully nothing too tricky here. So I think this is a good point to stop the first part. I'll go ahead and stop here, and then really for the most part we will just see some examples moving forward, and then we will get to some vector stuff towards the end of this section. So nothing too tricky, but I'll finish the rest of this out in the next part or two.